continuing our look at the geometrical representation of complex numbers and locus, or locus, however you say that word. Circles, we saw them before. There's our basic circle there, centered at the origin. Now, we said we could write that as z times z conjugate equals r squared, but now we have another way of writing it as well, because every point on that circle is the same distance from the origin. In other words, its modulus would be the same. So we could simply write it as the modulus of z is equal to whatever the radius is. Now, got to be careful with that one. It's the radius, not the radius squared, of course, because we're talking about the length of the vector. If we were to shift the center somewhere else, remember we could see it like this: z minus omega, z conjugate minus omega equals the radius squared. But now we could simply say this: the length of that vector is always r. So every point on that circle, its distance from the complex number omega would be the same. It would be r. It's a nice, neat way of describing the circle. So what is this circle then? Well, x squared plus y squared equals 16. I say, well, that's simply the modulus of z equals 4. If I wrote it in conjugate form, it would be z times z conjugate is 16. This one here, well, I've got to do a little bit of work here to get it in a form so I can read off where the center is and things like that. If we complete our square, there we go. So now I know that the center is -3, 2i. So z minus the center, we get z plus 3 minus 2i. We're talking every complex number. If we were to join it up to -3 plus 2i, that distance would be 5. In conjugate form, it would look like that. Let's go the other way. Let's find the center and radius of this one. Well, I can read that straight from it. So I know it's saying z minus the center. So the center, that would be, well, if I'm talking about a point, it would be the point 5, 1, or the complex number 5 plus I, and the radius is 2. This one's in conjugate form, but again, it's easier to look at the one that's not the conjugate, so I don't get confused. Z minus the center. So the center on that one is -4, -1. But when it's in this form, it's radius squared, so the radius would be 7. I look at this one, I don't immediately recognize what it is. I could factorize the 3 out. Don't know that really helps me that much. I still don't really recognize it. So okay, let's put into x and y so I see the Cartesian equation. Play around with it, and okay, again, a circle, because I notice the coefficient of x squared and y squared is the same. Playing around with it, there we go. Now I've got it in a form where I can read off there. So okay, the center is 1/4 minus 1/8. The radius would be 3√5 on 8. Z times Z conjugate plus 2 times Z plus Z conjugate equals 0. Again, don't immediately recognize it, but I know Z times Z conjugate is x squared plus y squared. Z plus Z conjugate would be twice the real part, so I get 2x, but it's 2 lots of that, so I get 4x. Okay, we've got a circle yet again. This time our center is at -2, 0, and the radius is 2. I suppose there's no surprise all of those turned out to be circles, seeing I headed the whole thing as circles. Let's look at lines. We saw horizontal lines. I could write as the imaginary part of z is equal to some constant number. And vertical lines, the real part of z is equal to some constant number. But there's a lot of other lines that aren't horizontal or vertical. Well, how do we deal with a line that's not horizontal or vertical? Now, what I do know is that any line at all could be the perpendicular bisector of another 2 points. I mean, there's lots of different points I could have chosen, but that would be possible. Now, if that's the case, what I know is then the distance from W1 to my line would be the same as the distance from W2 to the line. So any point on that red line, if I was to join it up to W2 and W1, they must have the same length. So in other words, those vectors would be equal. Now if I see something like that, the modulus of z minus some complex number is equal to the modulus of z minus some other complex number, I know I've got a line. It's not horizontal or vertical, it's going to be at some angle. Something like this. There it is. Z minus some complex number equals z minus some other complex number. I know that's a line. Question is, what is the line? Alright, I could go and use coordinate geometry. Put it in, expand out, tidy up, there's my line. But now we've got another way we could do it. Is it any quicker? Maybe, maybe not. Let's see. I do know it's going to be the perpendicular bisector of these 2 points, the point 1, 1 and the point -2, -1. So if I find the equation of that line, well, I'm going to need the midpoint. So let's find the midpoint. There it is, minus half 0. I'm going to need the slope of the line. The slope joining these two is 2/3. Therefore, the slope I want's -3 on 2 because it's the perpendicular bisector. Put it into my point slope formula. We get the same equation. Was it quicker? Possibly not. It's just another way of doing it. Where could that idea save me some time is something like this, where all they've said is sketch it. They never actually said find the equation. They just simply said draw it. So if I recognise that straight away, oh, it's the perpendicular bisector, I plot the 2 points in. -2 and 4, they're the ones that it's the perpendicular bisector of. Well, halfway between that is 1, perpendicular. I actually have got a horizontal line in this case. There it is. I've drawn a sketch, and in fact the equation of that one's very easy to find because it's a horizontal line. It's just y = 1. What about rays though? What would rays look like? So remember, a ray, we have 3 things. We have rays, intervals and lines. Lines are ones that keep going in both directions. Intervals have a definite starting and finishing point. A ray has a starting point but then goes off in some direction. So here we go. There's a ray. I know the angle it makes with the x-axis is theta. How could I describe this one? Well, the argument of every complex number on that ray would be the same because they're all going in the same direction. Argument of z is equal to theta. You'll notice the starting point, I've got an open circle because at the starting point I haven't gone anywhere yet. So it doesn't have a direction. It's the 0 vector, the one that has no direction, or every direction depending on how you want to think about it. So that would be the argument of z is equal to theta. If that starting point was somewhere else, that's okay. It'll just be the argument of z minus omega because every point on that ray I'm joining up to omega. So we say that particular vector, z minus omega, its argument would be theta. It's still that direction that it's going in. Now we can draw nice regions in the plane. We want to know every complex number that satisfies this. The modulus of z is less than 1 and the argument of those z's are in between 0 and pi on 4. Well, the first one I know is a circle, but it's less than, not less than or equal to, so just like coordinate geometry, we dot the boundary. That would be mod z is equal to 1. The argument of z, they're going to be rays. So there's the ray going off at pi on 4, and we also have one going off at 0. Now what I tend to do when my argument is either 0, pi on 2, any of those, I tend to extend past the axes just to make it clear where the line is. Using a different colour can sometimes be useful. Otherwise you lose it in the axis itself. Okay, so we're talking about that sector in there. However, there is something else I have to do. I should circle them, because again, remember when we're doing regions in the plane, it's only going to be solid if 2 solid boundaries meet. In this case, this is a dotted boundary. So that point is not included because both has to be on both of them, and it's not on the circle. Now I suppose technically I should have dotted my argument after that circle as well because they're not included, they're not part of the region. Let's sketch this one. Z plus 2 minus 2i is equal to 2. Okay, well that's just going to be a circle. I use this one to highlight something. Be very careful with your circles. Because this particular one, the x-axis and the y-axis are tangents. So don't get sloppy and that circle overlap the y-axis or the x-axis. We know the radius is 2. We know it's a tangent. So it should just be touching the axes. Now that's really hard when you're drawing your circles freehand, and unfortunately the rules of the HSC these days is you're not allowed to bring in a nice template to draw a neat circle or a compass, things like that. You're not allowed. So you have to draw them freehand, and so you just got to be very, very careful. Anyway, there's our circle. What are all the possible values of the argument of z? All the possible values. Argument of z is coming from the origin. So basically we draw tangents to the circle, and nicely that's already been done for us in this question. But they would be the extremities of the argument. So therefore I know this one is going between and including pi on 2 and pi. What about if we had to find the maximum and minimum modulus? here's how we do. You draw a secant from the starting point, which in this case is the origin, and you go through the centre. That will give you the minimum and the maximum. We just have to do a little bit of algebra here to work out. I think we know the distance to the centre is 2 root 2. We can work that out. We also know the radius of that circle is 2. So therefore the minimum must be 2 root 2 minus 2. And the maximum must be 2 root 2 plus 2. So to find your minimum and maximum, wherever the starting point in my one, it's 0 because it was just Z we were talking about. Draw it through the centre and then work out what those lengths are. Which now brings me to this question. 2021 extension 2 question 16C was the very last question in that particular year's HSC. And it was a stinker. You had to draw this region. It's defined by the real part of Z is greater than or equal to the argument of Z. Notice the capital A. So they talk about the principal argument. Oh, I should have just read the next line. They actually told you that. Okay. So the real part of Z is greater than or equal to, oh, I've made it a little a, but that's all right. But I know my argument is going in between minus pi and pi, so I've sort of covered that there with that statement. Let's work out the boundary of this curve. The real part of Z is equal to the argument of Z would be the boundary. So the real part of Z is x. The argument of Z, how would I work that out? Well, that would be the inverse tan of the imaginary over the real, y over x. Nope, I don't know what that looks like, so let's keep going. I'll undo the inverse tan. I get tan x is y on x, so y is x tan x. That is the boundary curve. What on earth does that look like? Okay, let's construct it. My red curve there is tan x, and obviously the blue one is y equals x. I am multiplying these two curves together. Let's work out where it's positive, where it's negative, that sort of thing. I also know x is an odd function. I know tan is an odd function. Odd times odd will give me an even function. So I know what I'm going to end up drawing should be an even function. Positive times a positive gives me a positive. I'm in that section there. Negative times negative. I'm in that section there. Positive times negative. Positive times negative. So that's where my curve exists. What do I know? I know I have to bend towards asymptotes, all those sorts of ideas. That is what this curve looks like. Now that's a very interesting shape down here. Sort of looks like it's inflecting, but that's all because it's, remember it was the tan curve, so it's sort of got that shape like a tan curve going in there. Alright, there are a lot of different areas to check here. Let's test the regions and see where we are. Okay, first quadrant. Now in the first quadrant I know the argument of Z is in between 0 and pi on 2. So let's test my point. I'll pick a point. I've picked a point that's on the asymptote. Because I'm talking about a region, points on the asymptote can exist in the region. It's not part of that function, but the actual region we're looking at, it certainly can. I need to basically pick a point that I know the coordinates of, and that's why I've picked one there, because I know the x value there is pi on 2. So pi on 2, 1, if I was to test that, pi on 2 is greater than the argument of pi on 2 plus I. Remember, that was the region. That is certainly true. I know I'm in that section there. Second quadrant. Pi on 2 is less than the argument of Z is less than pi. But hang on. All of the points in the second quadrant have a real part of Z which is negative. Then there's no way then that that real part is going to be greater than the argument. So no points in that section are included. Let's look at the third quadrant. In the third quadrant, arguments go in between minus pi and pi on 2. Okay, let's test a point. Again, I'll pick one where I know the x value. So minus pi on 2 minus 1. Is minus pi on 2 greater than or equal to the argument of minus pi on 2 minus I? Yes, it is. Therefore, I'm in that section there. And then I get to quadrant 4. Minus pi on 2 is less than the argument of Z is less than 0. But hang on. Now it's sort of like the opposite of what happened in the second quadrant. Every point here has a positive real value. So it's always going to be bigger than the argument. So every single point in that section is included. There is the section that we want. It looks something like that. Some notes about some of the other things I've done on this. Argument of 0 is always undefined. So if you go back to what the original equation was we were working with, 0, 0 is not part of the solution. I have to exclude that point. The interval from 0, 0 to minus pi 0 is not included. So remember, the argument of z at that point is positive pi. So it's not included. And the region does not actually end at pi, even though we had all these asymptotes. It will keep going, because what we're looking at is the argument of z is in between minus pi and pi. It wasn't that z was in between minus pi and pi. It was the argument of z. So all of these points could be included as well. So 1F from our textbook. I've also put some exercises from the old Patel book there that we can look at. Let's play.